Going back to a thin plate of metal and trying to find its mass. Let's say, though, that this particular thin plate of metal is shaped like a parallelogram. What fun. Maybe a parallelogram looking about like this. Let's identify these points. Let's say this is the 0.51. This is the 0.74. And if that's going to truly be a parallelogram, this better be the 0.23 right there. And say we've got a density function, delta of xy equals x squared y. Question is, what's the mass of this region here, this domain? R right there. You have the tools you need to solve for this mass right away. Let's solve this in the way that you would if I forced you to. Right now, I said you've got 1 hour to solve this for the mass. I bet most of you could figure it out, but you might feel a little confused at first. You'd want to break this up into 3 pieces, integrate over each piece, and then add the results. You could probably figure that out, and maybe even within 20 minutes. But if we're going to do that, we need the equations for these lines. The bottom line has got a slope of 1/5 and a y-intercept of 0. This line has got a slope of what? 3/2. Y equals 3/2. It's hard to tell what its y-intercept is, so a quicker way to find the formula is to effectively use point slope form and write 3/2 times x minus 5 in parentheses plus 1. So the -5 comes from the first coordinate and the +1 comes from the second coordinate. Expand this will be 3/2 x minus 15/2 plus 1 will be minus 13/2. The y-intercept is actually negative 6.5. This one's just going to be y equals 3/2 x. And this one is going to be y equals what? 1/5 x minus 2 plus 3. Using that point right there. Subtract the 2 because that's the first coordinate, and add the 3 because that's the second coordinate, which expands to 1/5 x. 3 minus 2/5 is 13/5. Y-intercept is 2.6. So those would be the limits of integration for the appropriate double integrals. Limits for the first integral for x goes from 0 to 2. For the second integral, x will go from 2 to 5, and for the third, x will go from 5 to 7. So x goes from 0 to 2, y goes from the lower limit here is the x over 5, and the upper limit is 3x over 2. Should define my delta function first, maybe. X squared times y. Put it in here. Dx or dy dx, careful to get that order right. For the next integral, x goes from 2 to 5. The lower limit is still x over 5, but the upper limit becomes this thing. X over 5 plus 13/5. And finally, plus integral from 5 to 7. Now the lower limit changes to 3x over 2 minus 13/2. And the upper limit still stays the same as the previous one, x over 5 plus 13/5. So I am integrating the delta function here over the entire domain. As the sum of 3 integrals, this should give the mass. Oh, before we figure it out, let's guess. How? Here's where I'm emphasizing the concepts. Let's make a contour plot of delta. Although if I want to just graph it over the parallelogram, I need the region function thing. And then make adjustments. We are plotting it over this parallelogram. So effectively we need to describe this parallelogram with inequalities. Is there a simple way to do that? Yeah, it's a little tricky though. Focusing first on these equations. Solve those equations effectively for y minus 1/5 x, which I'll write as negative 1/5 x plus y. They're effectively saying that quantity is between 0 and 13/5. Which maybe for simplicity's sake, we want to multiply everything by 5 and write as 0 is between negative x plus 5y and 13. That would be one way to describe what's being between those two lines. But we also want to be between these two lines. Focus on these things. And effectively subtract y from both sides and then do a little rearranging, like add 13/2 to both sides of this one. Seems like we could effectively say 3/2 x minus y is between 0 and if I brought the 13/2 to the other side, 13/2. Maybe make that a little simpler by multiplying everything by 2. Seems like to be in this parallelogram, both of these systems of inequalities need to be true. I think that'll work. Let's see. So I have to type those inequalities in here. So 0 is less than or equal to negative x plus 5y is less than or equal to 13. I also need to use a double ampersand that effectively means and. I want both sets of inequalities to be true. So I think this will work. I think I'll graph it or the parallelogram. Yep, there it is. Let's also add in more contours. How could I estimate the integral from this picture? I could try to estimate the average value, very roughly speaking, of the function and multiply times the area of the parallelogram. Highest function values in the upper right corner. You can see numbers there that are getting close to 90. Yeah, I bet the value of the function in the upper right corner is 90. Delta of 7, 4 is, no, 196. Why am I seeing them? Oh, I missed the 1 in the front. Okay, it was hidden behind the arrow. In the upper right corner, the value of delta is close to 200. In the lower left corner, the value of delta is 0. Over sort of most of the parallelogram, it's in lower values. The dark sort of overcomes the light, in a sense. So what I'm trying to say is probably the average value of this function is closer to 0 than it is to 196. If I had to make a real rough guess, 60, 70, 80, 90, somewhere in that ballpark. Let's just say, I don't know, 75 for the average value. What's the area of this parallelogram? Turn your head. Base times height. You could figure out the base by figuring out the length of that line segment. It'd be, I guess, square root of 26, close to 5. And the height by figuring out the length of that one, I'm just eyeballing it, maybe close to 3. Area is approximately 15. 75 times 5 should be, roughly speaking, the value of the integral. 1125, I'm sure it's not exact. I'd be happy with anything between, give myself some cushion, 700 and 2000. Oh, I was way off. Okay. The average value is less than 75 is what that means. In fact, the average value is approximately that much divided by 15 or so, closer to 30. Yeah, the dark is really overcoming the light. Don't take that as a spiritual metaphor. So 464.75 seems to be the mass. If the units of the density are grams per square centimeter, this would be in grams. All right, is there a different way to go? Is there a better way to go? That must be the point of what I'm doing here. Yes, there is another way to go. Effectively, you can use these inequalities here and here, and in particular the part in the middle, to define what's called a transformation. A linear transformation, in fact, for those who know a bit of linear algebra. Say u equals negative x plus 5y, v equals 3x minus 2y. Just using what's in the middle there, without the fractions, to define a transformation. Effectively defining two new variables, as we do with u substitution in calculus 2. Let u equal something. When you're doing substitution in calc 2, you let u or w or whatever letter you want to use equal, whatever it is, x squared minus 1 or something. Figure out du and use that. We're going to do that exact same thing here now in a two-dimensional integral, double integral, instead of a single integral. We need two new variables, though. However, to use this transformation, you do need to actually solve. So x and y are kind of like the old variables, so to speak. U and v are the new variables. These equations give you the new variables in terms of the old variables. You need to solve for the other way around. You need to solve for the old variables in terms of the new variables. You'll see why in a minute. So I effectively have to solve the system of linear equations for x and y. Which, if you know some linear algebra, you can do it with a matrix. Augmented matrix, those who know some linear algebra. But I'm not assuming everybody knows linear algebra and row reduction. So instead, we could try to do it using the equations themselves, which effectively is going to amount to elimination anyway. For example, if you multiply, say, what should I do? The first equation by 2, and the second equation by 5, what happens when you do so? You get a 10y there and a negative 10y there. Now, if you add the equations, the y's go away. You've eliminated the y. To get 2u plus 5v equals 13x. So x is 2/13 u plus 5/13 v. I've solved for x. Now use that to solve for y. You could, for example, plug it into that equation if you want, or the first equation, it doesn't matter. V would be 3x minus 2y is 3 times, in parentheses, 2/13 u plus 5/13 v minus 2y. I'm trying to solve for y. Keep that in mind. Simplify. You get 6/13 u plus 15/13 v minus 2y. Oh, not too much further to go here. Solve that equation for y. 2y will be 6/13 u. 15/13 v minus v is plus 2/13 v, because 15 minus 13. I think a 1 is 13 over 13. And that means y will be 3/13 u plus 1/13 v. So effectively, if I've not made a mistake, the so-called inverse transformation is going to be x equals 2/13 u plus 5/13 v, and y equals 3/13 u plus 1/13 v. Is it right? How can I check my work? One way is with solve. If I type solve with capital S, the original system, this one here, say, in curly braces, u equals, don't forget double equal signs, negative x plus 5y, comma, v equals 3x minus 2y. Solve that for x and y and expand. X is 2/13 u plus 5/13 v. Y is 3/13 u plus 1/13 v. Yes, correct. Once you've done that, once you've solved for the inverse transformation, then you use it. How? The function to integrate was delta of xy equals x squared y. In terms of these new variables u and v, replace x with 2/13 u plus 5/13 v, and replace y with 3/13 u plus 1/13 v, and simplify. And that's going to be a bit of a pain to do by hand, in part because you got to square the x, and then you also have to multiply by y. Let's have Mathematica do it. Notice what I'm doing here. I'm just plugging those expressions for x and y in terms of u and v into the delta function. Expand it to simplify. Yeah. Is this worth it? Well, maybe it's worth it if you use technology. 12 over 2197 u cubed plus 64 over 2197 u squared v plus 95 over 2197 uv squared plus 25 over 2197 v cubed. If I integrate this new function, do I get the right answer? And how do I integrate it? And what would the limits of integration be? The limits of integration are the really nice part. The limits of integration are 0 and 13 in both cases. These inequalities. I mean, they just happen to be the same, 0 to 13 in both cases. That's just a coincidence. They didn't have to be the same. The new limits of integration for the new variables u and v, for the new single double integral, not a sum of 3 double integrals, they're going to be 0 to 13 for both of them. I'm integrating that function. What, du dv? Yep, or dv du, and then since they're both 0 to 13, either order would be fine here. This is not quite going to be the right answer, though, unfortunately. There's one more thing we're forgetting. I'll show you it's not the right answer. 6,041.75, that's not the right answer. What's the one more thing that we're forgetting? We're forgetting to multiply by the absolute value of the Jacobian determinant of the transformation. Yeah, exactly. And not the original transformation, but the inverse transformation. What in the world is a Jacobian determinant? So again, this inverse transformation is x equals 2/13 u plus 5/13 v, y equals 3/13 u plus 1/13 v. The Jacobian matrix J of uv is a matrix of partial derivatives, 2 by 2 matrix. Upper left entry is the partial of x with respect to u. Upper right entry is the partial of x with respect to v. Lower left entry is the partial of y with respect to u. lower right entry is partial of y with respect to v. That's the Jacobian matrix. Maybe I should call that Jack instead of J, because our reading, which is not from our main text, but instead is from a link to something seemingly related to our main text, reserves the letter J for the Jacobian determinant. Maybe I should call this Jack. Jack with a no K. JAC is the Jacobian matrix. In this case, it does happen to be a constant matrix because these derivatives are all constants. 2/13, 5/13, 3/13, 1/13. The Jacobian determinant, which the reading calls just Jacobian, but I don't like that, is the determinant of the Jacobian matrix. Yes, this is weird notation. Determinant of this thing, it's a 2x2 matrix. Determinant's easy to compute. 2/13 times 1/13 minus 3/13 times 5/13 becomes 2/169 minus 15/169 is negative 13/169, which does simplify nicely to negative 1/13. That's the Jacobian determinant. Now, finally, what the theorem, the general change of variables theorem, says to do is multiply by the absolute value of the Jacobian determinant, positive 1/13. Let's see if it's right. 464.75, yay, it worked. The general formula that we are using here is the double integral over a two-dimensional region of a function f of x, y, dA is the double integral over some other region, call it R prime, of f of x of uv, comma, y of uv times the absolute value of j of x of uv, comma, y of uv dA. The absolute value, I spell absolute, absolute value of Jacobian determinant. This is the general change of variables formula where what is x of uv and y of uv? That's essentially the transformation, the inverse transformation, called G in the one-dimensional case in the reading. The transformation, or it really should call it an inverse transformation because we had to solve for it. In a bit sloppy notation, x equals x of uv, y equals y of uv. Really, I should give different names to those functions. I'm treating both x and y as variables and function names. For our example, the transformation was this. This was x of uv and this was y of uv. This is also written in the homework problems as g of uv equals x of uv, comma, y of uv. Though I actually prefer writing something else. You'll see sometimes other people write, oh, how about capital phi of uv? I actually prefer using a Greek letter here, partially just for fun, and partially because other people do. The capital G, the capital phi, it just represents this transformation. And it's a two-dimensional transformation. It's taking two-dimensional inputs and giving you two-dimensional outputs. If this is a general change of variables, It better work for special cases like the example we did. It also better work for polar coordinates. Does this work for polar coordinates? For polar coordinates, x equals x of, should I write UV? No, how about r theta? Is r cos theta. And y equals r, y of r theta is r sine theta. And the Jacobian matrix, Jac of r theta, again, I'm using Jac. The reading doesn't do that. Just to distinguish the Jacobian matrix from the Jacobian determinant, is this matrix of partial derivatives treating r as the first variable and theta as the second variable. Differentiate x with respect to r, get cos theta. Differentiate x with respect to theta, get negative r sine theta. Differentiate y with respect to r, get sine theta. And with respect to theta, get r cos theta. That's the Jacobian matrix. What's the Jacobian determinant? Which I'll just call J of r theta. One more time, that's different than the reading's going to do. They don't use a Jac anywhere. That's the determinant of this, which upper left product is r cos squared theta minus, that's the main diagonal product. The off diagonal product is minus negative r sine squared theta. That becomes r times, in parentheses, cos squared theta plus sine squared theta. 1, which equals r, which is the extra factor in the dA when you use polar coordinates, r dr d theta. That r there is coming from the r there. You really should only use this when you're thinking about a polar region where r doesn't go negative, because if you allowed r to go negative, then you have to take the absolute value of this thing, which when r is negative would actually become negative r. So that would get confusing. So when you apply polar coordinates with double integrals, we are always thinking of our region in such a way that r is not negative. And that's not a, you can make polar plots where r goes negative, but you don't want to do that when you're doing double integrals. So it is working for polar coordinates. There is a three-dimensional version of this where you get a triple integral over a three-dimensional solid and a corresponding three-dimensional solid in the new variables u and v, and you still have the same kind of abstract formula, but you have a z of uv and w instead. You have an x of uvw, a y of uvw, and a z of uvw. And the Jacobian determinant is the determinant of a 3x3 matrix. And yeah. But you can confirm cylindrical and spherical still work. What is R prime? R prime is the new domain of the new variables, u and v. It, for our example, it was u and v both going between 0 and 13. Is there a way to understand what's going on here beyond just doing the calculation and seeing that you get the right answer? Yeah? I'm going to use a capital phi. For example, this was, what? This thing here. That's a function of u and v. By the way, you can certainly plug points into this, like what is its value when u is 1 and v is 2? It's 12 13ths, 5 13ths. Can we plot this function? There's really two ways you could plot it. You could think of this as a vector field if you liked, and plot it as a vector field. And that would be good to do if we were integrating it. But we're not really integrating this function. We're integrating the f function. We're using this to transform the variables, so to speak. So it's better to think of it as a transformation. Parametric plot will plot functions, parametric functions of more than one variable. We've always used it for functions of t, time, to represent parametric curves. But we're going to see these last 2 weeks, it's going to be useful to use parametric plot with 2 parameters, often called u and v, like we're doing here. And see how, well, in this case, the square going from 0 to 13 gets transformed. I want to see a grid as well. What's the command I need for that? I think let's try mesh error true. I think that'll put some grid lines, so to speak, in here. So if I'm going to have an animation parameter. You see this is in the side of manipulate. I'm going to call the animation parameter lambda going from 0 to 1. If I enter this as is, all I'm going to see is a square, which with a bunch of grid lines in it. Oh, or parallelogram, actually. Never mind. That's the final image. I do see a parallelogram with grid lines, so to speak, that are parallel to the lines on the outside of the parallelogram. How can I see the square be transformed into the parallelogram? It's a little bit of a trick. I'm going to put an extra u comma v in here times 1 minus lambda, and then plus this phi function times lambda. So now we see the square. Imagine the square to be in the UV plane. What's the UV plane? Well, it's just another plane that you label the axes u and v with. And as lambda, the animation parameter here varies from 0 to 1, we see this square get transformed into the parallelogram that we integrated over with a little flip to it. See that? Watch it again. Just gets shrunk down and it flips right now over itself to come up with the ending parallelogram. What's going on here? Effectively, the Jacobian determinant, -1/13 for this example, has an absolute value that measures the amount of shrinkage. The final parallelogram has 1/13 the area of the original square. And the fact that we got sort of a flipping in there is reflected in the fact that the Jacobian determinant is negative. So effectively, we have to multiply by the absolute value of it, which is positive 1/13, to account for that. Maybe that's still kind of mysterious, but it's true. With regard to polar coordinates, here the Jacobian and the Jacobian determinant are both constants. A constant matrix up there for the Jacobian matrix, a constant determinant for the Jacobian determinant, which again, the reading that I'm going to assign online never refers to a Jacobian matrix. They do use a matrix, but the word Jacobian is referring to the Jacobian determinant. I like distinguishing between the two. That's a constant, but with regard to polar coordinates, both the matrix and its determinant are functions, not constants. What's going on there? That's focusing on the determinant, that's reflecting the fact that the amount of shrinkage or expansion of areas depends on what r is. It depends on how close you are to the origin. So for example, let's just copy and paste this. So this is the parallelogram example. I'll call it a parallelogram transformation. Let's copy and paste out and make modifications for polar coordinate transformation. So I'll change the letters too. I'll change it to r and theta. R times cos theta is x. R times sine theta is y. Enter that. You know, for example, if r is 1 and theta is pi over 3, then, oops, that's not right. I need an underscore there. There we go. 1/2 square root of 3 over 2 is x and y. If I make an animation of this, for sake of clarity, let's change the letters again. what happens, let's make the square smaller here. Let's actually theta would go from 0 to, oh, for example, pi over 2. What are we going to see? We're going to see initially a square, actually, if it didn't fail. There, okay. A square. What is the square representing? You want to think of the square as being in an r theta plane, which is just an ordinary plane with the axes labeled r and theta. R is going from 0 to 2. Theta is going from 0 to pi over 2, not as an angle, but as just a label on the vertical axis. It's a rectangle. Under this polar coordinate transformation, it transforms into a quarter circle. That's how we ordinarily think about polar coordinates in an XY plane. And the fact that the Jacobian determinant is R intuitively means that regions where R is close to 0, R is the horizontal axis here. This region here where R is close to 0 gets shrunk a lot because R is close to 0. And the Jacobian determinant is R. So they shrink down to close to the origin here, much smaller area. Whereas something over here where R is close to 2 gets expanded in area. The area of these curved rectangles, if you will, is much bigger. They get multiplied by 2. They're 2 times their original areas, approximately. So you can evaluate the Jacobian determinant at any individual point that you want. In this example, it's the function is R, so at an original point, for example, when R is, say, 1.9 or something, the value of the Jacobian determinant there is 1.9. That means a small little region near a location where R is 1.9 in this picture gets expanded in area by about 1.9 in the image over here. Whereas if instead of 1.9, you're at 0.1, then a small region near R equals 0.1 will have its area shrunk by a factor of approximately 10. Somewhere close to here, it might be 10. One of these wedges here, you have to focus on the wedges. The small little almost rectangles that have curved sides. Those things might have a small area that's a small multiple of the original rectangle. It's not a proof. It's intuition about what's going on. If you were truly going to prove this change of variables formula, it involves, well, lots of rigorous math that's difficult. I will tell you that it does involve also thinking about cross products. Do you remember back when we talked about cross products, that cross products can help you figure out areas of parallelograms? It's relevant here, actually. Maybe you don't remember that. Back first 3-4 weeks of class, we talked about dot products and cross products. And cross products can help you figure out areas of parallelograms. It's actually related to the Jacobian determinant. And cross products are related to determinants, so maybe that's not surprising. I mean, for 3-by-3 vectors, but you can think of 2-dimensional vectors as being in the XY plane and having a third component of 0. So you still can do the cross product of vectors in the plane by making that third component 0, as we have also talked about with scalar curve.